Okay, so we're gonna continue talking about gravity. Gravity is also called gravitational force because that's what gravity is, a force due to gravity. Please don't call little g gravity. That's the acceleration due to gravity. It's not gravity. So gravitational force, to distinguish it from other forces, we put a little subscript g on it, the force of gravity. Isaac Newton first came up with the modern concept of gravity when he was sitting in an apple orchard and an apple fell. And he thought about it. The moon was in the sky. The moon was in the sky, the daytime sky. And he just, a light bulb went off. And he considered that, oh, the moon is attracted to the earth just like the apple is. But the moon's not falling and hitting the earth, but the moon is falling. And he considered that the moon must have a very big tangential velocity to keep it from falling into the earth. But without that gravity, the gravitational force between the earth and the moon, without that gravity, the moon would fly off on a tangent. So the moon and any orbiting object is actually falling towards the object that it's orbiting, but it's going so fast forward that it misses hitting the ground. And so he's the first one that explained what orbiting objects, what caused objects to orbit around other objects. So they're showing A. This is really AC. Like an apple has an acceleration equal to 9.8 meters per second squared when it's falling to the ground. Okay, 10 meters per second squared. Okay, but the moon has an acceleration also. It's less than 10. We'll figure out later what it is, but that acceleration, that's what little g is. But up there, little g is much smaller than 10. But we'll calculate that later. But there is that acceleration due to gravity is also the centripetal force for an orbiting object. So the moon is going around the sun because of the force of gravity. The force of gravity is an inward pulling force inward towards the circle, the center of the earth. Okay, so the force of 1 pulling on 2 is equal to the force of object 2 pulling on object 1. Now, it doesn't matter the masses as to which force is bigger. The forces have to be equal. So if I were to ask you who applies the greater force on the other, you pulling the earth to yourself or earth pulling you to itself, the force is the same because it's Newton's third law. Action reaction forces are equal but opposite in direction. Okay, so look at what's in pink here. Sorry, it got jumbled up. Which applies the greater gravitational force, the Earth attracting you or you attracting the Earth? Okay, so like I said before, the force of you attracting the force of the Earth attracting you is the same as the force of you pulling on the Earth. It's in the same line. Let me draw that better. Okay, the force of the Earth pulling on you is the same as the force of you pulling back on the Earth. So why do these two forces, why is it that when I jump off a ladder, why doesn't the Earth come up to me and I fall to the Earth? Since the forces are the same. So, of course, the Earth doesn't even budge and I fall to the Earth. So why is that true? Well, F equals ma. So when I jump off a ladder, there is the same force accelerating me to the Earth as there is accelerating the Earth to me. But the mass of the Earth is so incredibly large compared to my mass that the acceleration of the Earth towards me is incredibly small. So my mass is so much smaller than the Earth that my acceleration is so much more greater than the Earth's acceleration towards me. Okay, they ask you for the units for big G, and you could figure it out from doing this equation. I'll just show you. Newtons equals the units for big G times kilograms over meters squared. So I'm going to cross multiply Newton meters squared over kilograms squared. Okay, so that's the unit for G. I don't really need to do that on my test. It's just in positive physics they had you do that. So let's do this problem. What is the size of the gravitational force? So F is what I'm looking for, Fg. Acting on a 1 kilogram object, which is 1 meters from another 1 kilogram object. So they're both the same masses. And here's, I say, I'd have to say center to center distance. You can't just say the distance between them unless they're really far away. So F equals big G, big M, little m over R squared. So 6.67 e to the negative 11 times the two masses are 1, so that's 1 times 1 squared, not that matters, over the distance between them is 1 meters, and that's squared. So really my answer is very tiny, 6.7 times 10 negative 11 newtons. So unless the masses are humongous, you're not going to be even able to measure the gravitational force between them. So right here we got two objects. There's the masses of the two objects. We'll call this M. This is bigger, so we should call that big M. Not that it matters yet. Doesn't matter. You can still call them. Doesn't matter yet. But I always make the bigger mass the big M. Gravitational attraction between them is, so there's the force of gravity. How far apart are their centers? So I'm looking for R. Okay, so FG looks like that. They're the same FGs, that's because that's why I only have one equation for it. Okay, I'm trying to tell you, this is going to be so much easier and less time consuming if you set the equation up before you plug junk in. So I'm trying to solve for R. So I'm going to cross multiply. And then I'm going to isolate the R. So divide both sides by FG. Then square root the other side. Okay, so that is what my distance is. Now I can plug it in. Okay, 6.67 exponent negative 11. That's what G always is. That's why it's called universal law constant. The mass is 2.5 e to the 5. M1, or big M, and the other mass is 3.4 e to the 3. And that's all divided by the gravitational force, which is 5.4 e to the negative 5. So I plug in 6.67 exponent key negative 11 times 2.5 exponent key 5 times 3.4 exponent key 3 divided by 5.4 exponent key negative 5. Okay, if you're using an exponent key, you don't have to put this in parentheses down in the denominator. If you're stubborn, you're doing 5.4 times 10 to the negative 5 power, then you have to put it in parentheses. But use the exponent key, it makes life easier. So I get this answer, but then I have to square root my answer. So what I get is the gravitational force between those two objects is 32.4 newtons. Okay, so here's F. I just call it F from now on. So FG. Their centers are, okay, this, the center distances are, determine each of their masses. Okay, well, they have equal masses, so M1, M2, they equal each other. Okay, so F equals G M over R squared. Okay, we're solving for one of the M's. Well, because the two M's are the same, right? I can just go I can replace this with M squared. And I could do that because they're both the same. Okay, I'm going to solve for one of the masses, so cross multiply. And then get rid of the big G. And then square root this to get rid. So I have mass by himself. So the mass is equal to the square root of F, which is 2.5 e to the negative 9 times r squared, which is 0.5, squared over g, which is 6.67 exponent -11. And then you just solve it. 2.5 exponent -9 times 0.25 or 0.5 squared. Then divided by 6.67 exponent -11. And then square root it. I'm getting 3.06 kilograms. So each of those guys is 3.06 kilograms. Okay, this is something we already did. So you can check your answer on the QR code. Okay, same thing with this. You can check your answer with the QR code. These are really easy, so I'm going to just let you check the QR codes. Okay, this is just awkward numbers, so we might as well solve this. What is the magnitude of the gravitational force? So that's F between Earth and Moon. This is the distance between Earth and Moon centers is R. Okay, so there's the mass of the Earth and there's the mass of the Moon. I'll call the mass of the Earth big M, mass of the Moon little m. Okay, so we're going to use the equation F equals big G M, big M little m over R squared. Again, these are all multiplied up here. Okay, so we don't have to rearrange this because I'm looking for the gravitational force, so I can use that equation straight. So 6.67 e to the -11 times the two masses, so 6 e to 24 times 7.3 e to 22. Divided by the radius squared. Please don't forget to square it. People do that commonly. They forget that squared right there. So I'm getting this answer to be huge. 2.02 e to 20 newtons. Even though the moon's pretty far away, the mass of two objects is so great that the gravitational force, even at that distance, will be humongous. 2.02 times 10 to 20 newtons to the force between the Earth and the moon. Okay, this is the same thing compared to the force between Earth and the sun to the Earth and the moon. Okay, so we're still trying to find the force. Okay, G is always 6.67 e to the 11 times the mass of the moon, of the sun, 2 e30, 2 times 10 to 30 right here. And then the mass of Earth, 6 times 10 to 24 over the distance between the Earth and the moon. The Earth and the sun is, that's far, 1.5 e to the 11 squared. Took me about a minute to solve for it. So I get 3.6 e to the 22 newtons. Comparing that, it's like 100 times, 100 times bigger. That's why we orbit the sun and not the moon. Okay, these are the kind of problems that I'll like to ask on a test because they don't take as long and you still understand what you're doing, hopefully. If the Earth's mass were to triple, okay, and the sun's mass were to stay the same, everything else stays the same. If you read on what happens to the gravitational force between Earth and sun, okay, write the equation that applies. So what if question, and then what's happening, the mass of the Earth is the triple. So I'll put a 3 right there in front of the little m. What does that do to the other side? So balance this equation. I just do the same thing on the other side. I'm not doing algebra. I'm just balancing the equation, as it were. So the force of gravity 3 times greater. It would be increased by a factor of 3. So the Earth would be pulled to the sun would be pulled to the Earth 3 times more than they were before. Okay, the distance between Earth and Moon goes 1/2, and everything else stays the same. What would happen to the gravitational attraction between Moon and Earth? Okay, so same equation. Okay, so R went to what? 1/2. So when I do the one side, I have to do the other side. But don't forget the squared. So this would be 1 over 1/4, right? 1 over 1/4, because that's what 1/2 squared is, which is equal to 1 times the inverse 4 over 1. So that'd be 4 times greater. So the moon would attract the Earth, and the Earth would attract the moon by a factor of 4 times what it was. Okay, so the distance between Sun and Jupiter was tripled. Okay, that's R. And Jupiter became 1/4 the mass. Okay, Jupiter is smaller than the Sun, so M becomes 1/4 of what it was. Okay, what happens to the gravitational pull? Okay, so F equals big G, big M, little m over R squared. So what happens? The radius was tripled. No, the orbital radius, the distance between Jupiter's center and the Sun's center, and the mass of the smaller planet compared to the Sun went to 1/4 of what it was. So we have to go to the other side and do the balance the equation. 1/4 on top, and then 3 squared on the bottom. You didn't forget the square, I hope. So 1/4 over 9 is equal 1/4 times 1/9. So really that really shrinks down to 1 over 36 times is 1/36, as big as it was. So it shrinks by a factor of 36. Okay, here's a new concept for you. Gravitational field is the same thing as the acceleration due to gravity. Okay, what is a field? Okay, that's another term. You need to know that. Gravitational field. Same thing as little g, the acceleration due to gravity. So you got to remember that. Okay, so any object, think about this. What is a field? Field is a strange kind of thing that we just take for granted. A field is something where if you put an object in that field, the object will start to move and accelerate on its own, it seems. So if I let go of a rock above the ground, I didn't throw it, it just starts accelerating towards the earth. And you say, well, what force is causing that? Well, we know it's gravity, but it's an invisible thing. Same with electric force, same with magnetic force. There is a field around anything with mass that pulls by invisible force other masses to it, that attracts other masses. And we can visualize this if we draw all the paths that an object could take when dropped anywhere, when let go anywhere above a bigger mass. All those lines would represent the field. Now, the closer the lines are to each other, the stronger the gravitational field. Okay, they come out here too, right? So I'm just trying to do a two-dimensional picture. So each of these lines is called a field line. And all the lines together is called the field, the gravitational field. Now, the closer the lines are together, closer as you get closer to the planet. See, I got almost four lines in that circle, whereas out here, same size circle, I only got one, just approximately. Okay, really, there's millions of lines. Okay, so the field is denser or stronger, closer to the surface. So really, little g is no longer a constant. Little g is the gravitational field. The gravitational field gets stronger, gets bigger as you get closer to Earth. As you get further, it shrinks. It shrinks. It never goes away, really. It just gets tinier and tinier and tinier as you get further and further away. Okay, so here's the equation for gravitational field. Okay, so here's how we figured it out. I did it right here. So gravitational force equals your weight. Gravitational force equals your weight. Gravitational force is this. I just been using that rule. And your weight is mg. Okay, so that's what I'm doing right here in this box. Okay, so the m's cancel out, and I'm left with an equation that's in this box right here. That'll be on your equation sheet. The gravitational field, g, or the acceleration due to gravity, is related to the mass of the planet that is exerting the field, a stronger field, divided by the distance between the object centers. So right here, an object would experience a bigger field of this big planet M than it would out here because it's closer. So let's use that equation to solve some problems. Okay, the vector is a vector, right? It's always pointing towards the object that's creating the field, the big M. Okay, we already said this all. Okay, so compute G. Well, G equals big G, big M over R squared. So just plug in your values. Very easy. 6.67 e to the negative 11 times the mass of the big planet. In this case, it's Mercury. 8.3 e to the 23. Oops. Then divide that by the radius. Okay, right? Radius is the distance between the surface and the center. So the radius of the planet is what you put in here. Usually it's orbital radius. Don't forget to square it. So I calculated it out to be 3.8. That's it, meters per second squared. So your weight would be much less on Mercury than it would be on Earth. Okay, here's my friend, the what if question, compute G. Okay, so write the equation that applies. Then you see what changed. Okay, the radius is doubled, so I had to double the R. And the mass of the planet is also double. So I have to go over to this side, put a 2 here, put a 2 squared on the bottom. So actually what happened is it went to 1/2, it decreased by a factor of 2. So it went to 1/2 times what it was before. Okay, 2 over 2 squared is 1/2. So it decreased by a factor of 2, or went to 1/2 what it was. So all you do is, where is the gravitational field the strongest? So where is little g the strongest? Well, obviously, if you use the equation, you just look at it. M is the same. M is the mass of the planet, the Earth. So it all depends on R. And the smaller the R, the bigger the gravitational field will be. So it looks like A is closest than any other one. Also, the arrows give it away. The arrows signify the acceleration due to gravity, G, or the field. So the bigger the arrow, the stronger the field. Okay, so you write what happens to the little g, the surface gravitational field. Distance from double, so it's 2r. Okay, so I write down the relevant equation. I already did. Then you just put the 2 in. This is a what if question. Once again, getting tired of them. Okay, so g equals 2 squared, or 4 times what it was. So it goes to 1/4 of what it was. It decreases by a factor of 4. Okay, what happens to the surface gravitational field, little g at the surface, if the mass of the planet doubles with no change in the radius? So the mass doubles. So put a 2 next to the mass. So little g doubles as well. You do it to the top. There's no square or square root sign. Determine the surface gravity. It's so badly written. The surface acceleration due to gravity of Earth. Okay, so surface gravity doesn't make sense. That would be your weight. That's not what they're asking. So they could have said the surface gravitational field. But anyway, okay, so here's big M, here's the radius of the Earth, and we're looking for G. So, well, I know the answer is 9.8, but let's solve it. Let's just see why. So, G equals 6.67 e to negative 11 times the mass. Sure you do the right. If you didn't label it, you might do this backwards. So I already labeled this as the mass, 6e to 24 divided by 6.4 e to the 6 squared. And I get 9.77, which basically is 9.8 meters per second squared. Okay, so basically, you can do this one. Surface gravity, I don't like that. The surface gravitational field, very poorly written. The gravitational field, or I could say the acceleration due to gravity near the surface of Earth's moon. Okay, you can solve that sucker. And look it up with this QR code if you want to. I'm going to say, do the same thing here. Determine the surface gravitational field of Earth's sun. Compute G for the surface of the planet, or near the surface, whose radius is double that of Earth, and whose mass is tripled. 2r. So, I can still do this a shortcut way without calculating it all. Okay, so the mass is 3 times bigger. Oops. Let's change that to a different color. The mass is 3 times bigger, and the radius is twice as big, so the G will be 3 on top and 2 squared on the bottom, fourth. So the G is going to be, G on the planet will be 3/4 as much. Now I don't see that answer. 3/4 as much of what Earth's is. So we know Earth's is times 10, because that's what G is on Earth's surface. So 30 divided by 4 is going to be 7.5. I knew that. So they used 9.8, so it's really 7.3. But yeah, I'll use 10 for positive physics and on my test to make calculations go by quicker. Okay, I already mentioned this, but as the distance increases and gets really, really big, the force of gravity gets really, really small, but it doesn't go to zero. And same with acceleration due to gravity. As the distance gets further, the gravitational field gets weaker and weaker and weaker, but never goes to zero. Okay, recall that in any equation, whether it's this one or this one for gravitational field, that the R is not just if you're in space, outside, well off the surface of the planet. The R is a distance between you and the center of the planet, not the surface of the planet. Okay, so if you're a height off the surface of the planet, R equals the radius of the planet plus the height off the planet. So, in either case, whether you're finding the gravitational force or the gravitational field, the R that I've been using, which I call big R, is the radius of the planet plus the height of the planet. Okay? I just don't like how they use capital letters for that. If you recall, so we have the International Space Station orbiting the Earth. It's manned by astronauts. You can see it in the sky every couple of weeks. So it orbits an altitude of about 350 kilometers. So the height is 350,000 meters. Travels at average speed. Okay, that's the orbital velocity or the tangential velocity. Okay, so we can find the gravitational force out there, or we can find the gravitational field out there just from the height and the radius of the Earth. We'll do a problem like that in a minute. But because it's so close to the Earth, I mean, that doesn't seem like it's that close, but really 190 miles off Earth's surface is not that far. So you can find that the G, the low acceleration due to gravity, the gravitational field is very close to what is on Earth's surface. Okay, in this problem, they have an orbiting object much further from the Earth than the International Space Station. You see that the orbital radius is 5 times the Earth's radius. So, right here, the Earth's radius is given, and then from the middle of the Earth to where it is 5 times what it would be if you were on Earth's surface. The height would be. So, orbital radius R is equal to the Earth's radius plus the height off the ground. So compute G. So G equals big G, big M times R squared. I'm sorry, divide by R squared. So that's 6.67 e to the negative 11 times the mass of the Earth. Remember, the mass of the satellite doesn't matter. 6 e to the 24 divided by the orbital radius, which is 5RE squared. Now a shortcut would have been doing this. Okay, we know on Earth's surface G is 10. Or near the Earth's surface. Well, this isn't near at all. So that make this a what if problem. So we're going to put a 5 here. And so this is going to, you can make the other side of the equation 5 to 5, put 5 squared in the denominator. So we know that G is 10, so it'll be 10/25. It'll be 1/25 of what it was. 1/25 times what it was. So that'd be, normally is 10 if you're on Earth's surface, but you're 5 times the Earth's radius away from the center. So that's going to be 0.4 meters per second squared. So if you want to do it the long way, like I started up here, you would just put 5 times, what's the radius of the Earth? 6.4 times 10 to the 6. In there for RE. So then you would square it. And when I do that, I get 0.39 meters per second squared, which is very close to what I got when I did it with the what if method. I just think the what if method is so much easier. So if I use the shortcut method here, gravitational field is big G big M over R squared. And R, by definition, in this problem, the height is 1 Earth radius, right? Well, the total distance, R, is 2 Earth radiuses. The shortcut method, the what if problem method would be, okay, so H plus the radius of Earth is 2 times the radius of Earth. So I put a 2 times the radius there. And so I'd have to put a 4 here. So R would be equal to 2.5 meters per second squared. Because it's 1/4 of what it was. And 1/4 of what it was is 10 if you're on Earth's surface. So that's 10/4, which is 2.5. Okay, but you could have done it. G equals 6.67 e to the 11 times the mass of the Earth. This takes a long time, relatively speaking. 6e to the 24 divided by the radius of the Earth, 6.4 e to 6 plus, well, another radius, 6.4 e to 6, or you could have said 2 times that squared. And when you get it, you should get the same exact answer or close. Okay, in this problem, the height is 2.8 times 10 to the 8 meters, but I don't know how many Earth radiuses that is, so I'm just going to have to work it out the long way. So the radius of the Earth plus the height is what R is going to be. So G is equal to 6.67 e to the negative 11 times the mass of the Earth, 6e to 24. divided by the radius of the Earth plus the height above the Earth's surface. Then don't forget to square that. And I get a very small value, well, of 4.6 e to the negative 3, which is 0.005, or actually 0.0046, which is 4.6 e to the negative 3 is really what I got. So there we go, right there. My calculator read that. So back to that problem about the International Space Station. So what is the Earth's gravitational field, little g, out there? We're there 350 kilometers above Earth's surface. So that's the height. So I can't really do a shortcut on this, like a what if question. I can't. Okay, so that'd be 6.67 e to the negative 11 times, what's the mass of the Earth again, 6 e to 24. Divided by r is the orbital radius, so that would be the radius of the Earth. Plus the height off the ground. So the radius of the Earth is 6.4 e to 6 plus the height off the ground, 350 kilometers. But I can't use kilometers, I have to use meters. And then square that value. So I get 8.78 meters per second squared, which is very close to 9. So it's kind of amazing that they feel weightless when they have such a strong gravitational field, being that close to the Earth. But they feel weightless because they're falling around the Earth. We just found that out, that it was like 8.8 compared to 9.8. So it's slightly less. So when we found the gravitational field, G, we found that it was pretty, like, very close to, what was it, 8.8 or something when we solved it. That's not that different from 9.8. So why aren't they falling and hitting the Earth? Well, it's because they're going so darn fast. Like I said, it was like a couple 100,000 miles per hour. In other words, they have a high, as the station's going around in its orbit, they have a high tangential speed. We call that orbital speed. And if it wasn't high enough, it would eventually fall to the Earth. It would go and hit the Earth. Now, they don't need rocket engines to keep it going, because that was the initial rocket launching velocity that gave it that speed. And then once they're an object in motion, they continue in motion according to the first law of Newton. So here they show the tangential velocity or the orbital velocity, that gives it the gravity Fg is the centripetal force, and the centripetal force causes a centripetal acceleration A. People get confused on this in positive physics. That centripetal acceleration of an orbiting object is the same as the gravitational field or the acceleration due to gravity. So that's an important concept that you should understand. If you're orbiting, your centripetal acceleration is supposed to be the acceleration due to gravity at that location, or the gravitational field at that location. And you're going to have to go, remember, AC equals V squared over R. So depending on how far you are from the Earth's center, you have to go a certain speed, velocity, tangential velocity, in order to have that centripetal acceleration. But that centripetal acceleration should be what the g is out there, the little g. So here's a picture that Newton actually drew, explaining that if you don't have enough, if you're launched forward like a projectile off a height, it's going to hit the ground. Give it a little more speed, and it will hit the ground further away. Give it a lot more speed, and it will hit the ground really far away. Give it just the right speed, and it will continue falling towards the Earth, but it won't quite make it because it's the correct speed to maintain an orbit. So what is the speed needed to maintain an orbit a certain distance away from the Earth's from a planet's or the sun's center? So all we had to do is equate the centripetal force on the satellite or the moon to the gravitational force, as we did right here. Okay, so that's the gravitational force. That's the centripetal force. And you can see that the mass of the satellite cancels out. So leaving the big M, which is the mass of the object being orbited. So mass of the orbited object Okay, so if I give you the mass of the satellite, don't plug it in for this equation. Always put the mass of the thing being orbited. So the two little m's cancel out. The little m cancels out on both sides, leaving this equation right here. And then square that, get rid of the square. So the orbital velocity, Vt, the tangential velocity, the orbital velocity, is equal to the square root of big G, mass of the orbited, times mass of the orbited planet, divided by the distance between the center of the planet or star and the satellite. Okay, so now this old equation, V equals the circumference over the period, T, that's the period, the time to do one revolution, one orbit. R is the orbital radius. So from the center to wherever the satellite is. Okay, so, and V is the orbital speed, as we learned and used before. So the equation we just derived right here, the orbital speed equation I'm going to equate these two equations as so, right there. Okay, this is very useful. This is called Kepler's third law. Now if I get rid of the square root, I square both sides, right? So 4 pi squared r squared over t squared. Okay, I did that to get rid of the square root up here. Okay, so this equals gm over r. So we can make this a linear equation if you want. Gm t squared equals 4 pi squared r cubed. And that's what I'll write on the equation sheet. But I've oftentimes just referred to it like this. T squared of r cubed equals 4 pi squared over gm. Okay, this is called Kepler's third law. But I'll write it like this on the equation sheet. We'll go into that more in a few minutes. Okay, so we're looking for the orbital velocity distance from the center, so I don't have to add it to Earth's radius. So that's just r, orbital radius. Okay, so this thing in the middle, the orbit object is big M. So V equals what? G big M over R. Simply plug in your values. 6.67 e to the negative 11 is big G times the mass of the orbit object, 7e28, divided by the radius, but don't square this time. So the calculation comes out to be 32,211. So I'll just round it right there. Meters per second. Okay, don't forget to take the square root after you do all the multiplication and division. Okay, so the orbital period is the time it takes to do one orbit. So we got R, we have the big M of the object being orbited. In the calculation we just did on the last problem, we have that as well. So basically all I really need, I can use my old equation, V equals 2 pi R over T, then TV equals 2 pi R. And so T equals 2 pi R divided by speed. So that'd be 2 times 3.14 times R. 4.5 divided by the velocity, 32,000. So I get this big number, 883125, which I'll round up. Seconds. Now, I could change that to minutes, hours, days, years. And you can always use Google to do that if it's a positive physics question. But when you use a physics equation time and period always has to be in seconds. Okay, when they say orbit, they're talking about the actual trajectory, the path of the satellite, that circle. Okay, so to have a stable circular orbit, it must have a velocity which is several things, but has to be tangential to its orbit, or else you'd be climbing out of the orbit or heading back towards, falling closer to the object that you're orbiting. So acceleration is a centripetal acceleration, and that always points towards the center. So I guess if is perpendicular to a tangent on its orbit. So that would be true. Okay, there's a tangent that line I drew, and AC is perpendicular to that. Or I could say perpendicular to the tangential velocity. I could say that. That's confusing. Okay, so I'm looking for V. Right here is orbital distance from the center, so that's R. And the mass, the big mass, is 3 times 10 to the 27. So, term of velocity. Okay, I'll let you do that. There's no tricks involved with that. You can check the QR code right there. Okay, so I pushed a button by accident, but let's talk through this. Okay, I'm looking for the orbital period. That's capital T. Objects orbiting a distance from the center, so that's R. And then the mass of the object being orbited is 3 times 10 to the 27. So that's M. So I'm going to use the Kepler's third law equation that I derived a few pages back. Whoops, I wrote this backwards. I just checked. 4 pi squared over GM. So we're solving for T. So let's get rid of the R cubed. Okay, so I'm going to multiply both sides by R cubed. Canceling it out here. Then I'm going to take the square root of that. Canceling out the square on the period. So the period is equal to 4 pi squared R cubed 7.3 e to the 8 cubed over 6.67 e to the negative 11 times 3 e to the 27. And I get 276898 seconds. Okay, that was kind of difficult calculation on your calculator, kind of time consuming, which I probably would round up. Okay, so this is really 2.8 e to 1, 2, 3, 4, e to the 5 seconds. So I don't know why they're getting it slightly different, but you're supposed to look at the next digit over to round. Anyway, now you might want to just do it this way, like we did before. V equals 2 pi R over T. After having found V equals GM over r. After you find that, you can plug into this equation and solve for period. Okay, but I like using Kepler's third law when I can, because it's one step instead of two steps. Oops. Okay, I forgot to push the button again. So, in the center right here, this equation is Kepler's third law. Now, Kepler's third law states that the relationship between the period and the orbital radius, right there, the period of a planet and the orbital radius of a planet around the star, like our sun, or the period of a moon over the orbital radius of the moon around the planet is orbiting. So, so we can see from this that there's a shortcut you can take if you're talking about one planetary system or one planet and its many moons. And that shortcut is this. Check out this box right here. Well, for a given system, big M's the same for all the planets going around there, because their mass doesn't matter. Big G's the same, 4 is the same, pi squared is the same. So that whole side, that box part of Kepler's third law, is a constant around a given M. So we could say that this ratio applies to any planet going around the same mass. So we could just like write it here to the left. T squared over r cubed is a constant for any planet. So we could say, okay, planet 1's t squared over r cubed ratio is the same as planet 3's t squared over r cubed ratio. So it makes it much easier comparing the different satellites going around a given object, orbiting around a given object. Okay, so in this kind of confusing picture, we have Earth right here. We got a satellite right here. And so that's called the satellite's orbit. RS. Okay? I'm sorry, the satellite's orbital radius, we'll call that RS. And then the moon's orbital radius, we'll call that RM. No, RM is 60 Earth radiuses in size. Okay, so I'm going to make that kind of a shortcut and use, instead of using this huge number. Okay, I want to know what is RS's radius, how many Earth radiuses away should I put this Earth satellite when I launch it, so that it's orbiting the Earth with a stable orbit. So, because both of these things are going around the Earth, I can say t squared over r cubed of the satellite is equal to t squared over r cubed of the moon, instead of using that GM 4 pi squared thing in Kepler's third law. This is still Kepler's law. Okay, so I'm solving for this. I know that the period of the satellite, I want it to be 24 hours. Okay, I can do days. Since I'm doing a ratio, this makes it easier. I can do days instead of converting them to seconds. So TS is 1 day, so 1 squared. So I'm going to do that right there. Okay, radius is what I'm looking for. Cubed. Okay, TM is 27.3 days. The period of the moon takes 27.3 days to go around the Earth once. And then radius of the moon, we said was 60 RE cubed. Okay, so cross multiply. 60 RE cubed is equal to the 27.3 squared times RS cubed. So, you know what? Why don't we just make this simple? Instead of RS, we're going to write question mark RE. Okay, because I want to know how many Earth radiuses is away. Now you could have just done 60 here and disregard the RE and then solve for X there. I mean, that would have been easier because RE is going to cancel out anyway. So 60 cubed RE cubed equals 27.3 squared times X cubed RE cubed, right? Because everything in the parentheses gets cubed. So the RE cubed cancels out, like I said was going to happen. And so we could have just disregarded it. So X cubed is equal to 60 cubed over 27.3 squared. Okay, so 60 cubed, 60 caret 3 divided by 27.3 squared. I get 289.82. Okay, and then x3 equals this. So I have to get rid of the cube root. So how I do that is I multiply it, the exponent, by 1/3. Because I don't have a square root button on a cube root button. But that's okay. So this is 289.82 to the 1/3 power. Now if you have a cube root, you just do that. So I take my answer and I caret parentheses 1 divided by 3 parentheses, and I get 6.617, 6.6 Earth radii. Well, I get 6.6, and then I interpret that, well, that satellite is 6.6 Earth radii. Much further than the International Space Station, much further. Okay, but not anywhere near 60 RE where the moon is. Okay, so the radius of the satellite is 6.6 Earth radii away. So the height would be, right, R equals 6.6 Earth radii away. So this would be 1 Earth radii. And then you'd have 5.6 more. And then this would be the height. The height would be 6.6 minus 1 is 5.6 Earth radii. So right here they're emphasizing that we like these kind of satellites that orbit the Earth in 24 hours, because what's happening if the satellites orbiting the Earth in 24 hours and the Earth's orbiting, the Earth's rotating on its axis in 24 hours, then that satellite is like a stationary object in our sky, wherever it is. So it's like a really tall antenna that we can send signals to, then broadcast, reflect back to radio dishes on Earth, then reflect back to other satellites until it eventually gets back to it gets to a receiver on Earth, like on the other side of the world or wherever. So these are we got a whole bunch of these satellites out there as antennas for our communication systems. This problem is asking us to find the orbital period of a satellite near Earth. No, I don't, that's very vague. Near Earth, well, maybe like the International Space Station. So let's say it's like, I don't know, 1/10 of the Earth's radius off the ground. So here's a satellite. Okay, so here's Earth's radius right there. Then the height is 0.1 radiuses of the Earth. Okay, so the orbital radius would be 1.1 Earth radii. Okay, so what is the period of the satellite? So how many times does it go around the Earth? What's the time it takes to go around the Earth? The period. Is a constant. If I know something other satellite that's out there, and I know the moon, so let's call the moon the other satellite. And then this man-made satellite, we'll just call S. So remember how RE cuts out, so let's not do that extra step. So I'm looking for T of the satellite. So TS squared, I could just put X squared equals 1.1 cubed, right? I'm getting rid of the RE because it's the same on both sides of this ratio. The period is 27.3 days squared of the moon, and the moon is 60 cubed. So what I do is cross multiply. So TS squared times 60 cubed is equal to 27.3 squared times 1.1 cubed. Okay, so I'm going to divide both sides by 60 cubed. Now look, I didn't put the RE in. It already canceled out the RE. like I said before. Now I'll get rid of this square on the t by square rooting this side. So I get for my calculation 0.068. And that would be what, days? So this satellite's zipping around the Earth. Okay? So 0.068 days, how many hours is that? 0.68 days, you don't have to do this. 1 day is 24 hours. So it takes like almost an hour and a half to go around the Earth once. Okay, so it's moving much faster than the moon is in its orbit. Okay, so you should be able to just look at this ratio. Tell me which planet's moving faster. Okay, so if t squared over r cubed is a constant for a given mass, then the one with the bigger radius will obviously have to have the one with the bigger period. And the one that has the bigger period is obviously, it takes more time to go around, is going slower. So who's the fastest planet? Mercury's the fastest. Who's the slowest planet? Well, Pluto's not considered a planet, but we'll say Pluto is the slowest. When I say slow is v, the lower v, orbital velocity, but that means a long period. So the fastest is Mercury, fastest, that means a high orbital velocity, but also the smallest t, because it's going so fast, the time to go around once is small, the period is small. So using Kepler's third law, if we know the period, the time it takes to go around the sun for a planet, which you can observe in the sky every night, you can figure that out over time. Then you can figure out how far that planet is away using this equation. So we got an idea of the size of our solar system once Kepler came up with this third law. So we could, here's Jupiter with all its moons. Well, no, with some of its moons. It has about 100 moons. 125, 150, I don't know. Okay, so by knowing how far these are, each of the moons were, and how long they took to go around once, we could figure the mass of Jupiter from that. Okay, so very powerful equation for understanding things in our solar system and outside it as well. Okay, here's a trick question. Okay, satellite A has twice the mass of satellite B. They're orbiting a planet with the same orbital radius. Okay, so both the radii are the same. The orbital period of satellite A, so T of A compared to T of B. Well, if you recall, T squared over R cubed is a constant for both of these. Well, they have the same R. And if these are equal, if A's T squared over R cubed ratio is the same as B's T squared over R cubed ratio, which it has to be because they're orbiting the same planet, Well, the t's have to be exactly the same as well. So I have to conclude that TA squared equals TB squared. So the period A has to equal the period B. Now you might get confused if you don't do this right. T squared over R cubed equals just realize that in this equation, m is the mass of the object being orbited, not the mass of the satellite. The mass of the satellite does not have anything to do with its period. So the answer is the same, period. T squared over R cubed is a constant for a given orbital system. So, if you have a bigger R, like planet 2, you have to have a bigger period. Because T squared over R cubed has to be constant. So for planet 2, you got a bigger radius, but to match the T squared over R cubed for planet 1, if you increase your radius, you also had to increase your period. So you get the same ratio as the T squared over R cubed for the other planet. Two satellites orbit the same planet. One has an orbital radius which is 4 times larger. Okay, T squared over R cubed. Okay, so one has an orbital radius 4 times larger. Its orbital period will be what? Okay, so I'm assuming these are 1s. So cross multiply. So 1 times 4 cubed equals x squared, question mark squared, times 1 cubed. Okay, so what we got is 4 times 4 times 4, I don't know. So x squared equals 4 cubed. So x is equal to the square root of 4 cubed. So see if I can do this on a calculator. This is the same thing as 4. Actually, yeah. 4 squared times 4, right? And so this is square root of 4 squared is 4. And the square root of 4 is 2. So we get 8 times greater. Now you could use your calculator. Okay, so the period of the moon. Okay, that's Tm. So orbital radius is 3.8. So that's the moon's orbital radius. So radius of the moon. What would be the orbital radius of object orbiting Earth with a period of 20 days? So if that's the radius of the satellite, what would be the orbital radius of that satellite? Oops. 20 days is the period of this satellite. What would be the orbital radius? So RS. So T squared over R cubed equals T squared over R cubed for the moon and for the satellite. So 27.3 squared. Plugging in values. 3.8 e to the 8. And that whole thing is cubed is equal to 20 days, 20 squared for the satellite over, I'm looking for this guy. So cross multiply, 27.3 squared times R. I could just call that X equals 20 squared times 3.8 e to the 8 cubed. Get rid of the 27.3 squared. Then get rid of the cube, because I'm trying to solve for the orbital radius of the satellite. So I'm going to raise that to the 1/3 power to get rid of the cube. So I get the orbital radius of the satellite to be 3.08, 3.1 times 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8 meters. Whoa. So that's this answer right there. Okay, what's the orbital period in days of an asteroid orbiting the sun with an orbital radius twice the radius of Earth? Okay, so since we're both orbiting the sun, the asteroid and Earth can use this Kepler's third law. So I'll make this the asteroid. I'll call the object the asteroid. Okay, and then this one will be the Earth. Doesn't matter which one. Okay, so the asteroid period is, let's just call it X. And it is twice as far from the sun as Earth. So I'm going to just put 2 for the R, the asteroid, cubed. And so the Earth's period is 365, let's say 365 days squared. And then the radius, the Earth's orbital radius is just 1 cubed. So x squared times 1 cubed, I'm going to cross multiply, equals 365 squared times 2 cubed. So that cancels out because 1, then just find the square root of that. I calculate that out to be 1032 days. Okay, so here is a problem similar to the one we just did, except they're using something called an astronomical unit. AU is an astronomical unit for distance. And it makes this kind of problem much easier than using actual, like, meters. Okay, so by definition, 1 AU astronomic unit is equal to it equals the orbital radius of the Earth. So if this was the sun, this is the Earth, this distance right here would be 1 AU, 1 astronomical unit. So, let's do this problem. If Neptune's orbital distance from the sun is 30.11 AUs, how long does it take to complete its orbit in years? Okay, so this is kind of really easy when you have AUs. So we're looking for Neptune's period. Okay, well, you might say, well, where's the other one? Well, it's Earth's. Okay, we know the Earth's radius and the Earth's period. You might say, I don't know the Earth's radius, I have to look that up. No, the Earth's radius is 1 AU. Okay, so I can put 1 cubed there. And then I can put, for t squared, I can put 1 squared because I'm doing years. There's the period of the Earth around the sun is 1 year, so 1 squared because that's Kepler's law. And then do it for Neptune on the other side. I don't know what the period for Neptune is. That's what I'm looking for. How long does it take to complete its orbit? So that's what I'm looking for. But put a square next to it because that's part of the equation. Then the Neptune's orbital distance from the sun is 30 Earth distances, or AUs. So 30.11 cubed. So at this point, cross multiply, 30.11 cubed equals x squared. The one's just 1. I'm not going to write those. Anything times 1 doesn't change things, so I don't write it. So let's get rid of the square by square rooting the other side. And I get 165.2 years. So Neptune takes about 1.5 centuries to go around its orbit.